Hello friends, hello everyone. Welcome to another video from See Feel Academy, where we learn together from each other. So in this video we will discuss about a well-known algorithm, Prim's algorithm, for finding minimum spanning tree. So this video assumes that you know some basic concepts of graph. If you want to refresh your concepts, you can do so. I already have a video for refreshing those basic concepts. If you want to do it, you can do it over here. So let's start with Prim's algorithm. So let's see what a minimum spanning tree is first. So a minimum spanning tree is a subset of edges of a graph. So a spanning tree, that is a subset of edges of a graph that forms a tree, and it includes every vertex of the original graph in such a way that the total weight of all the edges of the tree is minimized. So a spanning tree where if we add up all the weights of the edges in the tree, we should get the minimum value. So Prim's algorithm is a greedy algorithm, which means at every step it tries to optimize. At every step it will only choose the edge that has the minimum weight, assuming that it yields a tree which has the minimum weight at the end. And it works for a weighted undirected graph only. In fact, we normally don't have concept of spanning trees or a minimum spanning tree for directed graphs. And it so yeah, how does the algorithm work? So intuitively what this algorithm does is it actually starts with a vertex and it builds the tree with one vertex at a time. So we pick a vertex, we add another vertex in such a way that the edge that we have chosen is actually a minimum, and initially we start at an arbitrary vertex, and at every step we just keep adding a new vertex in such a way that the possible connection that we choose is actually cheapest or the minimum one. So on the right hand side we can see a graph where the minimum spanning tree is highlighted. So it actually covers all the vertices, it doesn't leave any vertex, and it is a tree, which means there is no cycles in it. So minimum spanning tree has a lot of applications, which I would suggest you to look at on the internet or to various resources for various resources, and I'll also see if I can link some resources here in this video so that it might make sense how important it is. So let's dive into how the algorithm works and a little bit of history about the algorithm. So this algorithm was very first found in 1930. That's quite long back, and it was found by Czech mathematician Jarnik. In fact, that's one reason why we also call it as a Jarnik's algorithm. But it wasn't published, it wasn't made available to the public till 1957, when actually an American mathematician, Robert C. Prim, published it and made it available to the public. On the right side you can see a visual representation of how the spanning tree is built. So the nodes, the small dots you see are the are the vertices, and at every step you can see the existing tree is expanded to add a new edge as to cover all the vertices. And as soon as we cover all the vertices, we are done. As soon as we have identified the tree, we are done. So how does it work step by step technically? So it starts with initializing a tree with a single vertex. In fact, just choose any arbitrary vertex at first, and then in every step just grow the tree by just single edge. Pick one edge which is minimum from the current set of vertices that we have to the set of vertices which are not there in the graph, and then include that vertex and that edge to our current minimum spanning tree. And then we just repeat the same process over and over again till we actually cover all the vertices in the tree. Once we have covered all the vertices, we are done. So let's apply it to an graph and then see, because then it will be a lot more clear. So here we have a graph where we see 6 vertices A, B, C, D, E, F, and weights on every edge. For example, AB has a weight 1, AC has weight 2, BC has weight 3, and so on. So the problem is, so we need to find the MST, or the minimum spanning tree, of this graph. So let's see in iteration 1 what we need to do. As we discussed already, initially we'll just pick a random vertex, but usually, because by convention we choose A, we'll just choose A. So let's say A. So A is currently part of our minimum spanning tree. So what is the next step? Now the next step is to see how many edges are there from our current spanning tree to the rest of the graph. So let's see. From A we can see there are 2 edges, AB and AC. There are only 2 edges possible, and edge AB has weight 1, edge AC has weight 2. So what do we have to do? We have to pick the lowest possible weight of the edge, or edge that has lowest possible weight, and then just include that edge in that vertex. So here the choice was pretty easy, because AB had 1, which is the lowest. We'll just pick AB as our edge, and our tree now grows from just A to AB, and in fact it includes node B. So we choose B, and here is our tree AB. So our current spanning tree is AB, and which has only 1 edge and weight is only 1. So move on. Next we just repeat the same process over and over again till we cover all the vertices. So let's see in the step 2 what we have to do. Now since we have two vertices A and B, we need to consider all the edges that start from A and all the edges that start from B to the rest of the graph. Now remember, there is no need to consider AB again, because AB is already part of our spanning tree. So let's see what edges are available to us. So from A we have AC, from B we have BC. We have no other edges, and we need to pick the minimum one. Now the minimum one from here is AC, which has weight 2. So we just pick the edge AC and expand our tree from AB to C. So we include C. So now our spanning tree consists of 2 edges and 3 nodes, A, B, C, and the weight of our spanning tree is the sum of weight of edges inside the spanning tree, which is 1 plus 2, which is 3. So it looks easy, huh? Move on to the next step in the similar way. So again we need to select edges with lowest weight from the tree. So let's first see what are the edges available. So now since our tree has expanded and we have more number of nodes, we'll have more edges. So these are the edges available. From B we have BC, from C we have CD, from C we have CE and CF. So there are 4 possible options, and the weights are BC is 3, CD is 4, CE is 5, and CF is 6. So let's see now what do we have to do. Our algorithm says we have to pick the minimum one. So the minimum one from here is BC. So we'll pick minimum one BC. But no, we cannot pick BC. Why? Because if we pick BC, we are no longer left with, we don't have a tree. ABC becomes a cycle, and remember, a tree cannot have a cycle. Hence, we cannot pick BC here. Because if we pick BC, we'll form a cycle in our existing MST, and hence we have to ignore BC but pick the next available minimum edge. So we ignore BC and then we pick the minimum from CD, CE and CF. Now in this case the minimum is CD, which has 4. So we expand our tree, we choose CD, we find, and we expand our tree to now contain D, and our total weight is now 3 plus 4, 7. Now notice what we did here. This is an important step. We couldn't take BC because BC forms a cycle with the existing edges we have taken. Alright, moving on. The next step. So there are still 2 more vertices to be covered, EF, and we again start first of all listing down the edges that we have from our current MST. So we'll have all these edges again BC will come, CF will come, CE will come, and a new edge DE will come. DE has weight 7. So again the same strategy, we cannot include BC for the same reason we couldn't earlier, and from the remaining edges we pick CE because CE has weight 5, which is the minimum, and we expand our tree to include the node E. So the total weight of the tree now becomes 7 plus 5, 12, and we are almost there. In fact, there's just one more vertex to be added and then we will be done. Moving on, following same iteration steps again. Now we have 5 nodes in our current tree and we'll see all the edges that we have. So we have edge BC, we have CF, FE, which is a new edge that got added, and DE. Notice again we cannot take BC, but then we have to take the minimum of CF, FE and DE. So CF has 6, FE has 8 and DE has 7. So the minimum one from here looks like 6, which is CF. So we'll pick CF and then we'll include it in our current tree. So this gives this final tree, and the weight of the tree increases to 12 plus 6, which is 18. So looks like we are done now because we have included every vertex. And notice what we ended up with. We ended up with a tree which actually covers every vertex of the graph, and it actually has a minimum weight, which is 18. So thank you friends for listening to this video. I hope this video helped a bit or helped a lot to explain what Prim's algorithm is. And definitely do mention any questions or any comments you have, or if you have any suggestions for new videos that I could explain. Alright, thanks friends. We'll see you again in the next video. Bye.